Hi, my name is Carmen Muller-Karger. Today we will talk about spring, mass, and damping element to model mechanical systems. Some of the figures and content of this presentation are adapted from our textbook from Ingreso Route, the Mechanical Vibrations 6th edition. The learning objectives of these presentations are to compute equivalent values for spring elements, mass elements, and damping elements. All mechanical systems and structural systems can be modeled as mass spring damp systems. Most practical vibration systems are very complex, and it's impossible to consider all the details for the mechanical model and the mathematical model. Therefore, we have to find equivalent systems, simplified systems, to be able to do a study or analytical analysis of our system. So today we will focus on how to convert a real system in a mechanical system. So we will be finding the equivalent constant of the springs that represent our real system. In this case, we have the suspension and the mass of this motorcycle with the person on it, and in this case we have the wing of an airplane modeled as a cantilever beam with a mass in the end. That mass could contain the mass of the wing and, for example, mass of engines attached to the wing. And after we have a mechanical model, we can do a mathematical model, get a solution, and do the analysis. The spring elements are one of the elements that accumulate potential energy in our systems. A spring is a type of mechanical link which in most of application is assumed to have negligible mass and negligible damping. The force produced by a spring is related to an elongation or a compression of the length, and it opposes the displacement of the end of the spring. The force is given by the constant of the spring times the displacement, and this displacement is the finite length minus the unstretched length. And when we are compressing the spring, that compression will also be the unstretched length minus the final length of the spring. The work done by the spring, that could also be calculated as a potential energy, is given by this expression right here, which is 1/2 the constant of the spring times that displacement of the spring squared. This value is always positive because this distance, it doesn't matter if it's extended or compressed, this distance is to the square value. Most springs using a practical system exhibit a nonlinear force deflection relation. It can be seen in this graph. This is the deflection and this is the force, and the force of the spring can be given by this expression right here. If the nonlinear spring undergoes small deflection, it can be replaced by a linear spring. We calculate the constant of the spring by the derivative of the force of the spring respect to the displacement evaluated at the position where we want to use our spring. That will be probably the equilibrium position of the system. Some systems involving 2 or more springs, like this case over here, may exhibit a nonlinear force displacement relationship, even though the individual springs are linear. If this mass or weight travels and we have a clearance C1 and C2, once the mass hits or compress one spring, then we'll be in this side of the force displacement curve, and if the weight displaced to the other side and covers the clearance C2, then we'll be in this side of this force displacement graph. This is a piecewise function and is linear in some part of the curve, in some part of the graph, but the total behavior of the spring respect to its displacement is a nonlinear relationship. Let's calculate the equivalent spring constant of a uniform rod of length L, cross-section area A, area moment of inertia I, and Young modulus E. We can do it to two different cases. The first one is when that uniform rod is subjected to a tensile or a compressive force. Then we will have an elongation of that rod, which is denoted by delta. If we multiply and divide by the length of the rod, we can substitute the elongation divided by the length by the strain. And remember that the strain is equals to the stress divided by the E modulus, and the stress is defined as the force divided by the cross-sectional area. If the definition of the constants of the spring is force divided by the deflection delta, then doing some algebra we can find that the constant of the spring of a uniform rod of length L, cross-sectional area A, and Young modulus E can be defined as A times E divided by the total length of the rod. In the second case, we have a cantilever beam subjected to a transversal load at the end, at the free end. We want to substitute this system by an equivalent constant of the spring and a mass. As you recall from mechanics of material, the displacement of the end of the beam is defined as the weight, this weight over here, the length cube divided by 3, the E modulus, and the I, which is the area moment of inertia. Using the same definition for the constant of the spring, force divided by the deflection, we can find that for this cantilever beam, the equivalent constant of the spring can be written as 3E, the modulus E, I divided by the length cube. Here there is a table where you can find the two equivalent constants that we just found for a uniform rod subjected to a tensile force and a cantilever beam with a mass at the end. And this is how you calculate the area moment of inertia. And then we have, for example, here a simple support beam. If you just do a similar analysis, you will find that the equivalent constant of the spring is 48. The Young modulus times the area moment of inertia divided by the length cube. In the case that we have shaft subjected to a torsional moment, we will have an equivalent torsional spring that can be calculated as the G constant of shear, J, which is moment of inertia, divided by the length. We will find many examples in which we have several springs, and some of them are what are called in parallel, or some of them will be in series. So here we have 3 different rods, and this will have an equivalent constant of the spring. This one will have another constant of the spring, and this will have another constant of the spring. In this case, we have 4 springs that are in parallel. So in this case, they are in series, and in this case are in parallel. So let's calculate how is the equivalent constant of the spring or of springs that are in parallel and in series. In the case that we have spring in parallel, what these two springs have in common is that they experience the same displacement. Therefore, the force will be different because the constant of the springs are different. So the force that this spring experiences will be K1 times the displacement and this will be K2 by the same displacement. I want to find a equivalent system that has only one spring with an equivalent constant of the spring times the same displacement. If we make these two systems equal, we will have that if we add forces in y direction, this will be the weight will be compensated by these two forces. We are doing a statical analysis, therefore we don't have acceleration. We have that the weight is equals to adding those constants together equals to the displacement. And if we do the same for this system, we get this expression. So since the weight are equal in both, we can say that this that is in the bracket is equals to that. By conclusion is that when we have spring in parallel, you add both constants to get an equivalent constant of the spring. In the case that you have spring in series, the spring experiences different displacements, but since we don't have a mass between those springs, and you do a free body diagram of this point and analyze the forces, you can see that the force that they experience is exactly the same. So in spring in series, both springs experience exact the same force. And what we want to do is make this system an equivalent system as this one right here. Since all forces are the same, the force experienced by the first spring is equals to the force experienced by the second spring. The force experienced by the second spring is the constant of the spring times the relative displacement between the two ends. And this will be equals to the constant of the spring equivalent, constant of the spring times the total displacement of this mass over here. If we solve for the first displacement and introduce it in the second here, in the second spring right here, we can say that this force is equals to the weight because we are in equilibrium. Then if we solve for the displacement for this system and we solve for the displacement for this system and make those two total displacement equal, and we solve, we can see that when we have spring in series, the inverse of the equivalent constant of the spring, it will be equals to the summation of the inverse of each of the constants. In our vibrating system, we have the cycle of converting kinetic energy to potential energy and back to kinetic energy. We already studied the elements that produce potential energy. Now we can study the elements that produce kinetic energy. Those are mass or inertia elements. We will assume that the mass or inertia elements are rigid body, and they can gain or lose kinetic energy whenever the velocity of the body changes. For single degree of freedom system, for this simple analysis, we can replace several masses by a single equivalent mass. The key is to choose properly a parameter that will describe the motion of the system and express all the other parameters instead of the chosen one. Calculate the kinetic energy of the system and make it equal to the kinetic energy of the equivalent system. Let's remember what are the equations to calculate kinetic energy. When we have a rigid body in poor translation, the formula to calculate its kinetic energy will be 1/2 the mass times the linear velocity of the center of mass squared. If we have a rigid body but now in poor rotation, which in this case is because we have a pin over here and this body is rotating respect to that fixed point, the kinetic energy will be calculated as 1/2 the mass moment of inertia respect to that point P times the angular velocity squared. We can have systems that are in general motion, and those are the ones that are translating and rotating at the same time. In this case, we need those two components. We need the component of the linear velocity, and if we calculate the linear velocity of the center of mass, we have that the kinetic energy will be 1/2 mass linear velocity of the center of mass squared plus 1/2 mass moment of inertia respect to the center of mass times angular velocity squared. If we have also a rigid body in general motion, but we want to use any point, not only the center of mass, but any point to calculate the kinetic energy, then we have three components. 1/2 mass velocity of the point square plus 1/2 mass moment of inertia respect to that point, omega squared, which is the angular velocity. And we have this third component. This is the linear velocity dot product angular velocity cross mass, and this is the distance between the point P and the center of mass. So in general, the kinetic energy can calculate it using this expression. Of course, these terms can be simplified if you use the center of mass. And for example, here we have two masses connected by a L-shaped device, and it's fixed over here. So if these three have mass, but they are connected with a rigid weightless link, even though we have three masses, we have only 1 degree of freedom. So the total kinetic energy of this system will be equals to the kinetic energy of the first sphere, the kinetic energy of this L-shaped device, and the kinetic energy of this mass over here. Just to show an example, we have a bar over here that has a pivot point O, is a fixed point, and the bar is rotating in respect to the point and has three masses attached to that rigid bar. And we want to find the kinetic energy of the system to find an equivalent mass of the system. We will calculate the kinetic energy of the three masses, so the first one, the second one, and the third one, and we will choose one of the variables as the parameter that will describe the motion of the system and find the equivalent kinetic energy with respect to that mass. And that variable will be equals to my equivalent variable. And it's dot because we are considering it in terms of velocity. So if we describe a system in a general position, we can express the displacement of the second mass in terms of the first mass by similar triangles, and the displacement and therefore the velocity also of the third mass instead of the velocity of the first mass also by similar triangles. That will give me that I will place an equivalent mass of the whole system at the position 1, and I will call that the equivalent velocity of the system. So if I substitute x dot 2 by in terms of x dot 1 and x dot 3 in terms of x dot 1, I have this expression right here, and I can take out the common value x dot 1, and I have this expression right here. And since this is also my equivalent velocity, then I can say that what is in the bracket is my equivalent mass of the system. And that is how I find the equivalent mass to have a much simpler system. As a second example, we have here a pinion, which is a gear that has mass moment of inertia, G sub 0, and we have a rack. The rotation of this gear, since these 2 points have the same velocity, will be a function of this linear velocity over here. We can calculate the kinetic energy of the system as the kinetic energy of the rack which is a linear kinetic energy, and then the kinetic energy of the pinion, which we have a rotational kinetic energy, right? If we choose as a parameter x1, then we have to put theta dot as in terms of x. And if we do that, we substitute theta dot in terms of x dot. We get this expression. Now we can take x dot out of the parentheses. And here what we have in the brackets will be our equivalent mass if we chose to use x, which is the velocity of the rod, as our parameter that will describe the system. We could have also chosen that our equivalent parameter to choose the motion of the system is actually the rotation of the gear. In this case, we have the same expression for the kinetic energy, but now we will substitute, instead of substituting theta dot, we will substitute x dot. So we substitute x dot in terms of theta dot, and now we take theta dot out of our parentheses as a common variable, and then whatever here we have in the bracket will be our equivalent mass. As you see, this expression is not the same as this expression because we chose different variables to describe the motion of the system. Now we come to the damping elements. Those are responsible for the energy dissipation of the system. In many particular systems, the vibration energy is gradually converted into heat or sound. Due to the reduction of energy, the response, such as displacement of the system, gradually decreases. We will consider three types of damping. The first one is the viscous damping. The damping force is proportional to the velocity between the two ends of the damping and the constant that describes the characteristics of the damper. It's very important that if we do not have relative velocity between the two ends of the dampers, there is no force done by this damping system. The second type of damping that we see, or energy loss that we see in a system, is the column or drive friction. And as you recall from statics and dynamics as well, the force is proportional to the static or dynamic coefficient of frictions times the normal. The normal force will be calculated by the external forces that are in the system. And here you recall that we have the static portion of the curve and the dynamic portion of the curve. In the static portion of the curve, the force can take any value from 0 to the maximum frictional force, which is in the impending motion. And here the force takes the value of kinetic coefficient of frictions times the normal force. The last type of damping that we will have is the material or solid or hysteretic damping, and is due to friction between the internal planes, which slips or slide, and that deformation that occurs inside their bodies. Well, we have a hysteretic loop, and that will describe the energy loss in the system. Those equations will be presented in the next presentation. In general, the force of the viscous dampers can be expressed as the constant of the dampers times the velocity. When we have a nonlinear damper, we can find the linearized constant of the damper by deriving the expression of the nonlinear damper in terms of the velocity, and we will have to evaluate that for a specific position. We did that for the spring, and it's very similar. And then, as we did for the springs, we will have dampers in series, and the equivalent constant will be the inverse of the constant will be the summation of the inverse of each of the constant of the dampers when we have in series, and in parallel, when they have the same velocity in the two ends, we will have that we can add the two constants. We can calculate, for example, the damping constant of two parallel plates separated by a viscous fluid. you record that according to the Newton's law of viscous flow, the shear stress is equals to the viscosity of the fluid that is between the plates and the gradient of the velocity. That is this gradient over here, right? And we can say that this gradient over here, which is linear, here we have a fixed plate, here we have a moving plate, that gradient can be expressed as the slope of that profile. If the area, the surface area is A, this is the area of the plate, we can express the force as the shear stress times that area. And if we substitute the expression that we found out for the shear, we have this expression right here. And since we know that the force of a damper is the constant times the velocity, we can take all the terms that are not the velocity, and those will be the constant of the damper for two plates parallel that are moving. One is fixed and the other one is moving. We can do a very similar analysis, but in the case of two plates, but in this case we have a rotating shaft. Those will be hydrodynamic bearings. In this case, the velocity, the linear velocity of these plates will be, because of this rotation, will be omega r, and the distance, the gap that we use as h in the previous examples, now will be the distance between the shaft and the hydrodynamic bearing. And if we substitute this expression, and the area will be now 2 pi r L, because it's a cylindrical shape, we will get that the constant of the spring can be expressed in these terms. As you see, that constant of that damper will be a function of the viscosity of the fluid. It will be a function of the radius of the shaft cube. It will be a function of the length of the bearing, and it will be inversely proportional to the gap between the shaft and the bearing. With this slide, we conclude this presentation where we talked about springs, mass, and dampers, and we were able to find equivalent constants of the spring, mass, and dampers for different configurations.